My name's Ben Stucky, so I'm a math professor at Beloit College. You can call me Ben. Please just call me Ben. And everything that I'm going to be talking about today is joint work with Christopher Lloyd Simon at the Advanced Math Research Institute in Rennes in France. He's a postdoc there, and he and I have been, so he introduced me to this universe of problems, and we've been thinking about it together for like the last 3 years or so. And I've also it's a accessible enough problem that I've been able to work really effectively with some undergraduate students at Beloit, both math and computer science majors, including Eric So, Ryan Pham, and Araf Israk. So I'll touch a little later on some of the ways that they've contributed specifically. But yeah, so let's get started. I'll give a brief outline. So first, I'm going to talk about the preliminary notions, which is loops and pins. I'll describe this game from the title of the talk. And then I'll spend most of the time talking about how we take this game that's all about kind of topological notions, loops, and convert it into something that's purely cast in terms of Boolean logic, um, which is very nice. And then I'll finish by talking about sort of the hardness or easiness, the computational complexity of how hard it might be to decide who has a winning strategy, which is related to how hard it might be to make AI to play this game or something like that, or how hard it is for humans for that matter. So that's the goal. So I'm going to use pretty informal definitions here. This can all be made precise in the language of topology, but that's not really important for understanding what's going on. So a loop, for our purposes, is just a closed curve in the plane that can cross itself many times. And for simplicity, I'm going to restrict to loops that intersect in double points. So you have places where locally you have like a plus sign where two local pieces of the loop are touching. In principle, you could have like an asterisk pattern where you have like three local strands crossing at a point. That makes the combinatorics a little bit harder to talk about and study, but basically everything I'm going to say can be done in that setting. It's just simpler to restrict to loops with double points. And a basic question you'd ask is if you have a loop in the plane, you want to do some stretching, some compressing, but no tearing. So tearing is forbidden, and then find a way to untangle it. That's the goal. And it turns out that part of the nice thing about casting this in terms of loops with double points is that you can make this entirely combinatorial, and you can show it can be shown. It was shown by Haas, Scott, de Graaf, Schrijver, that these three moves are all that you need combinatorially to untangle any loop. So you have the R1, which stands for Reidemeister 1, which is just like pulling a kink out, basically. You have R2, which is like two local strands overlapping, and you pull that apart. I'll frequently refer to this shape in the R1 as a monogon, because that region inside there is like a one-sided shape. And I'll frequently refer to this shape as a bigon, because that shape is two-sided. So you can remove a monogon, you can remove a bigon, and there's a third move, which is this triangle move, where you can slide a strand across a crossing if you have a trigon or triangular region.
Sorry,
And
quick question.
yeah.
So for R2, I guess you're assuming that like the loop the loops like don't intersect with each other necessarily, so like they don't form a knot because like it's not really shown what the elevation level of the loops
Yes.
is in R2.
Yes, yes. So this is distinct. That this is not the same question, not the same universe of knot theory. And yes, I'm not distinguishing between a height. This is not a three-dimensional picture. It's a purely two-dimensional picture. Um, and but you raise an interesting point here, because there's so if you so this theorem says that the number of self-intersection points basically can always go down, right? As you're untangling. If you study knot theory, if you do any knot theory, you'll learn that you know that that's not true in knot theory. You can have a complicated loop that's tangled up in three-dimensional space, and you can define the analogous Reidemeister moves for knots. I think this is actually what was defined first. And for knots, the number of crossings may actually have to go up before it goes down. In other words, you might have to do some R1s or R2s in reverse before you go back down. So that is a very important and nice distinction to draw between loops and knots. Does that answer your question?
Yes, thanks.
Yeah. Um, Yeah, so this was shown by Hascott and de Graaf Schrijver. I have a demo here. So this is a JavaScript port of I guess it was originally a Java applet, where Richard Vaughan and Joel Hass actually implemented this algorithm, this curve shortening flow. And I'll draw a loop here. See if I can get it right. Uh, this is my favorite loop, if you can't guess from looking at my avatar. And if we start the disk flow here, this is going to basically apply the construction of Hass and Scott, which is algorithmic or can be made algorithmic, and reduce intersections. Okay, it's going pretty slow. I'm going to speed it up a little bit. Okay, so here you can see there's maybe a Reidemeister 2 or a Reidemeister 3 that's about to happen. Looks like they're going to basically happen at the same time. Yeah, so Reidemeister 2 and 3, and the number of double points decreased from 9 to 7. And it's continuing to go down, so it looks like we're going to have a Reidemeister 2 up here, and then a Reidemeister 1 soon after that. So there's a Reidemeister 2, and there's a Reidemeister 1. Then Reidemeister 2, and one last Reidemeister 2, and now the curve has no self-intersections. Sort of an aside, but very interesting. This is a extremely simple algorithm. All it does is it covers the screen with like a square grid. You draw the loop intersecting that grid. You look at the intersection points between the loop and the grid, and you just connect those intersection points with straight lines. Then you take the whole grid, you offset it by 1/3 in the x and y direction, and you repeat. And that's the whole algorithm. You just keep taking the grid offset and intersecting. So that's very nice. By the way, I will share these slides so that you can play with this. It's also linked from my GitHub page, which you can probably find. Okay, so that's fine. That kind of covers the case when you have just a loop in the plane. But now we want to talk about pins, and pins are basically obstructions that we introduce that are going to make it harder to untangle the loop, or maybe impossible. So the idea of pins is you can think of them as obstructions or punctures or whatever you like, but you're not allowed to move the loop through the obstruction. So in particular, if you have a pin inside of a monogon or inside of a bigon, you're not going to be able to do a Reidemeister 1 or a Reidemeister 2. If you have a pin inside of a triangle, you can't do a Reidemeister 3. And that leads pretty quickly to the following notion, which is pinning sets and pinning numbers. So take your loop in the plane and take some set of pins and try to untangle it. Do as many Reidemeister moves as you want, and you can do so as long as there's no pins blocking you. And if no matter what you do, you can't decrease the number of intersections, which means basically you can only ever do Reidemeister 3 moves, then that set of pins is called a pinning set. And you can associate maybe a cost with each pin and say, okay, now I want to use the fewest number of pins to pin the loop. And maybe I have some pinning set, but as soon as I take away a pin, it is no longer a pinning set. Such pinning sets are what we call minimal. And you could have a priori minimal pinning sets of many different sizes, and the size of a smallest pinning set, basically the absolute fewest number of pins that you need, is what we call the pinning number. So those are some notions, and here's the first question that I'll open up to you to basically guess. So here's a loop. What do you think is the pinning number of this loop? How many pins do you need? So please feel free to guess. Don't be afraid to be wrong.
I'm guessing 3.
3. All right. 3. Okay. Any other guesses? 2. So it definitely has to be at least 2, because you have this bygone region over here on the left, and you have this bygone region over here on the right. Anybody think it's bigger than 3? Yeah. So yeah, Zai. At least 3 is correct. So Zai, you're right. And Ben, you're right. You need at least 3. In fact, you need 4. So I will explain the algorithm. But I'm just kind of giving you the answer here. So you can show that the pinning number of this loop is 4. And moreover, there are 2 minimal pinning sets of size 4. And in fact, there are also minimal pinning sets of size 5. And there's 3 of them. So there are in total 5 minimal pinning sets for this loop. And here the way that you can read this is that capital A is a minimal pinning set. So you pin region 1, region 3, region 4, region 6. That will pin the loop. Or capital B, you pin 1, 2, 8, and 4. Or little a, you pin 1, 3, 7, 8, 4. Those are all minimal pinning sets. What goes wrong with 1, 3, 4? Good question. So here is the problem. There is a composite bygone. If you look at this, if you focus on this intersection right here and this intersection right here, you have a bygone that is kind of making a integral sign, like So so you got this strand here. Basically, the regions 5, 6, and 8. You have to pin at least 5. You have to pin at least 5, 6, or 8. Yeah, yeah. Which is okay. So this is already getting close to the Boolean formula, because yeah, you have to have at least one pin in one of those regions. Okay, but yeah, no, it is tricky, right? This is a small loop, and already you have this complexity, and so this is a hint that maybe this is a hard problem to solve. One thing,
real quick before you move
yeah,
on,
yeah.
maybe I'm misunderstanding your definition here, but you said 2 minimal pinning sets of size 4 and 3 of size 5.
Yeah.
Sorry, maybe I just misread it. I thought you were saying 3 minimal pinning sets of size 5, but they're not minimal. They're just 3 sets of size 5.
No, they are minimal. So if you have pins in little a, so if you have 1, 3, 7, 8, or 4, you can't take any of those away.
Oh, minimal but not minimum. Gotcha. Okay.
Yes. So yes. So So computer scientists will use this language of minimal versus minimum, right? So it's minimal under containment, but not minimum in the sense of the minimum cardinal.
Gotcha.
Yeah.
Yep.
Yeah.
Thank you.
Yeah. Exactly. Yeah. Okay. So, you can start to now look at the structure of pinning sets. One observation you can make is if I have a pinning set, I can always add more pins. That will keep the pinning property. So you could say that the set of pinning sets are closed under union or absorbing under union. You can always add more pins, and if you iteratively form joins, or add pins to pinning sets, you get this like partially ordered set structure where each node represents a pinning set, and you have them stratified by the number of pins in the pinning set. So at the top here we have the set of all pins, which is trivially a pinning set, because there's absolutely no Reidemeister moves you can do if you have all the pins. But taking away pins and going down, you may have a pinning set still, or you may not. But if you recurse down this structure, you'll eventually arrive at all of the minimal pinning sets. And this structure is what we call the pinning stack of the loop. Is there no utility in defining a pin outside the loop? That's a great question. So it depends on the surface. So for most of what I'm saying today, no, because we're talking about the plane, and so okay. Let me say first, if this is on the surface of a sphere or something like that, then you can go around the back, right? And so you could have a this could be like stereographic projection, if you've heard of that. The outside boundary of the loop could be like a triangle, and you could slide around the back of the sphere, basically. But if you're in the plane, there's no ability to slide around the back, and so basically the infinity functions as a puncture. Yes. Yeah, so if you're asking pinning questions on the sphere, then you absolutely have to consider the region at infinity.
So insofar as a pin is a puncture on the sphere, I guess like what we're doing here is just putting this on different topologies. Like
yeah.
insofar as every pin is a puncture, then that's like we're just changing the topology that the loop is on.
Exactly. You can imagine that everything I've said so far is happening on the sphere with a certain number of punctures. And if you want to restrict to planar loops in the plane, just put a puncture in a region that you call the infinite region and fix that for all time. You can ask these questions, by the way, on any surface, and I'll say a little more about that later too. Other questions, comments before I move on?
I'm just wondering,
Yeah.
for that utility that you showed before, is there a way to add pins and see what, whether it can still kind of unravel to a circle or not?
Uh, to add, I'm sorry, I didn't understand the question.
So at the start you kind of demonstrated you had a loop that was applying like the R1, R2, R3
Yeah,
transforms, right?
yeah,
To get back to a circle. Is
yeah.
there a similar utility or does that one have the capability to add pins so that you can kind of
Oh,
see where the sticking points are for
oh, yeah.
pending sets?
You're sort of asking, can you adapt the like Hascott demo and put pins in?
Yeah.
I would love to do that. I've thought about that. There's challenges with that. And uh, so I think it shouldn't be hard so you still have the theorem. That is to say, if you put a bunch of pins, the curve shortening flow still exists as a theorem. That you only need moves that decrease the number of intersections or don't increase the number of intersections. But computationally, it is tricky to implement because if you have if you have some pins, the portions of the loop are going to get caught near those pins, and you're going to have a hard time distinguishing between strands that are caught near those pins. So it's sort of a software engineering problem. Like I think you could code something up, but it wouldn't be very aesthetically pleasing because you'd see things just kind of getting stuck on the pins, and the finer picture would be harder to see. But it does exist in theory. Does that answer your question?
I've vaguely heard about Ricci flow. Does that possibly also work for this?
So I think don't I'm like 90% sure of what I'm about to say. I think the Ricci flow, like a mean curvature flow, does not guarantee the monotonicity. And I don't have a good reason why, but I think that is true.
What is monotonicity?
As in like if you perform something like a Ricci flow, the number of intersections might increase before it goes down. So
Uh,
it will eventually become a circle, but you might you might introduce more intersections on the way,
oh, and
depending
are you
on your
suggesting
initial
that the
configuration.
the demo that you have there never does that?
It never does that. That's right.
Interesting. Okay.
Yeah, yeah.
So it's necessarily taking a path that that always reduces the amount of intersections.
Yes,
I
yes.
see. Gotcha.
Yes, thank you. Thank you, Stacked Overflowed. When I say monotonic, I mean that the number of intersections is not increasing. Yeah. Other questions? Okay. So on to the first theorem. So given a loop, you want to compute its pinning number. How hard is that computationally? How hard is it to compute the pinning stack? The first theorem that we proved was that it's probably hard. Probably the best algorithms that are going to compute the pinning number are exponential running time. Specifically, we showed that it's NP hard. The decision problem which takes a loop as an integer, a loop and an integer as input, and decides whether the pinning number is less than that integer, That is an NP hard problem. And so I don't want to harp on the finer points of computational complexity, but suffice it to say that if you found a fast algorithm to compute the pinning number, then say a polynomial algorithm to compute the pinning number, then you've shown P equals NP, this famous problem in computer science, which is widely it's believed that P is not equal to NP, so there's probably not a polynomial algorithm. Okay, just to Quark asks, are R3 moves by the demo always required, or can you sometimes avoid them with other moves? So the demo is not combinatorial. The demo is the demo does not guarantee configure there may be configurations where you have multiple points. You have like 3 or 4 strands all crossing at the same point. So no, so strictly speaking, the demo does not exactly give you the Reidemeister sequence. You'd have to make some choice, kind of resolving those singularities to extract a Reidemeister sequence. Or expand the types of combinatorial moves that you allow. Yeah, exactly. Also, if you have a multiple point, so you have a crossing where 3 strands cross, you have to count that as 3 crossings. If you have 4 strands crossing there, you have to count that as 4 choose 2 crossings. If you have 5 strands, you have to count it as 5 choose 2 crossings. Anyway. How are loops encoded in the decision problem? So we can take combinatorial embedding of a graph in the plane, say a 4 regular graph in the plane. So you can take a list of vertices. So take like an adjacency list where every vertex has 4 adjacencies. But you want to record the cyclic order, and that's enough to recover the picture. Weakly or strongly NP hard. You're gonna have to remind me what that means. I don't come from a computational complexity background, so I'm not totally versed on the difference there. We reduce from vertex cover. So and I imagine that it preserves many of the properties of vertex cover. So whatever vertex cover is, it is probably that. I'm not sure about that. Do you know if vertex cover is weakly or strongly NP hard? I know vertex cover is fixed parameter tractable, and so I imagine this is fixed parameter tractable. Okay. Yeah. So I would guess that if vertex, I would guess it has most of the properties of vertex cover, but again, don't quote me on that. I'd have to read up on that and see if it applies to R reduction. Anyway, okay, so I think I'm going to move on. So, well, any other questions? I don't want to rush it. Okay, so now on to the unpinning game. So so let's play the following 2-player game. We start with a pin. So we start with a loop. We start with a pin in every region, and let's remove pins. And let's do it in such a way that a valid move has to leave a pinning set. If taking a pin away allows the intersection to decrease, or makes the set of pins not a pinning set anymore, then it's not a valid move. And the first player who has no move loses. So let's play here. We have 1, 2, 3, 4, 5, 6, 7, 8, 9 intersections, and we start with pins everywhere. And player 1 and player 2 are going to go back and forth. So player 1 is going to take away maybe this pin in the middle. It's an awesome game. I like it too. So take away that pin for player 1. Now player 2 is maybe going to take away this pin. Player 1 is maybe going to take away this pin. And it turns out at that point that you have a minimal pinning set, and so player 1 wins. If player 1, if player 2, for example, takes away this pin, then you can do a Rightemeister 2 on that bygone down there on the bottom right and decrease the intersection. So for this particular sequence of moves, player 1 wins, and the pinning stack that I discussed before, where you have all pinning sets, every game state corresponds to a valid pinning set, and every valid pinning set corresponds to a game state. So the pinning stack, if you've seen 2Swap's video about Connect 4, the pinning stack is that graph, that graph of all possible game states. And moreover, it's stratified. You're always starting at the top, and you're always moving down the stack. And all of the winning positions are the low, the lowest nodes on the partially ordered set that is the pinning stack. And yeah, so a question you could ask is, who wins for this game? That I'll ask. Anyone care to take a guess? So player 1 won in this example, but maybe player 2 has some sneaky way to win. Anybody want to guess? This is incomplete. Yes, thank you. So this is not the entire game tree, because actually this game tree is only the states that I formed from taking the union of pinning sets, of minimal pinning sets recursively. So for example, if I take the union of little b and capital A, I get to this guy. If I take the union of little a and big A, I get to this guy. If I take the union of little c and little a, I get to this guy. And then the union of this guy and this guy is this guy. And yeah, so this doesn't show, for instance, this only shows 5 as a first move. If I did 2 as a first move, that game state is not represented here. 2 out of 8. First 2 out of 8 lose. Can you clarify what you mean by that, Zai?
Oh, sorry, I mistyped. I was just trying to type in whether the first player wins in each move. Like, if the first player picks 2 or 8, then they lose. I was just trying to, yeah.
Yes, I agree. I agree. If the first player picks 2 or 8, it's a lose. In fact, I'll claim that 5 is the only winning move. And I guess I spoiled the answer there. So yeah, it turns out that player 1 has a winning strategy, and further that 5 is the correct first move. So we'll come back to this example once I've defined the Boolean logic. All right, so let's get into that. So so returning to the more basic question of when is the loop pinned, we have to pin what I'll call regional monogons or bigons. We have to always put if you see this, you have to pin it. If you see this, you have to pin it. But additionally, if you have a monogon that has other pieces of the loop crashing through it, you have to pin at least one of those regions too, right? Otherwise, you could just pull the loop across all of them and reduce intersections. And same thing for bigons. If I have a composite bigon of this sort, I have to put a pin in at least one region there. And it turns out that you can make this precise. So you need a suitable notion of composite monogon and bigon, which is a little subtle. I'll say why. But for a suitable notion of composite monogons and bigons, it's a hard theorem of Haas and Scott that if there is a pin or a puncture inside every one of those, then the loop is pinned. And so yeah, so for this loop, as we saw from our first example, it has 1 is a bigon. The region 4 is a regional bigon. 3 and 8 represents a bigon with so I'll call the vertices the crossings that are adjacent to a bigon. I'll call those marked points. So the marked points of this 3 and 8 bigon are here and here. Can everyone see my cursor when I hover my cursor?
Yep.
Okay, good. Okay, so for 2 and 3, we have marked points there and there. 2, 6, 7 is one of them, and this is the mirror image of the bigon that I mentioned earlier, where you have a marked point over here and a marked point over here. And because every single one of these regional bigon of these composite monogons or bigons has to have a pin for the loop to be pinned, and conversely, the loop is pinned if and only if every one of these has a pin. You can write down this positive Boolean conjunctive normal form where all of so the numbers here now become variables, which can be set to true or false depending on whether or not you have a pin, and the clauses correspond to these composite monogons or bigons, which henceforth I'm going to refer to as Moby disks, mo for 1 and bi for 2, and disk because they bound a topological disk. And so the theorem, which basically follows from that hard theorem of Haas and Scott, is that the loop is pinned if and only if the Moby disk CNF is satisfied by the corresponding assignment. So for instance, we saw that 1, 3, 4, 6 was I claimed to you that 1, 3, 4, 6 was a minimal pinning set, and now I'm saying it's a minimal pinning set because it's also a satisfying assignment. If you set 1, 3, 4, 6 to true and everything else to false, then the CNF becomes satisfied. Because this clause is satisfied, and this clause is satisfied, and this clause is satisfied. So the V represents OR. So 3 is satisfied, therefore this clause is satisfied. 3 is satisfied for this one. 6 and 6 makes them all satisfied. And the minimal pinning sets are minimal satisfying assignments. So I don't. So yes. So that's a good point. I am only using positive literals, and I don't need to encode negation. I'm just if so this satisfying assignment is 1, 3, 4, and 6 are true, and all the others are false. I don't need to encode negation. The theorem is write down this conjunctive normal form. It's always positive because you have a positive clause for every Moby disk. And the theorem is there's a one-to-one correspondence between satisfying assignments of this CNF and pinning sets. Yes, this will show that it's in NP. That's the theorem that I'm getting to. Yep. Yep. Yeah. Yeah. So I'll come back to that. Now, there's an interesting connection to dualization here. So here I've represented the 5 minimal pinning sets as letters, and a set is pinning if and only if it covers one of these minimal pinning sets. So at least one of the minimal pinning sets must be pinned in order for this loop to be pinned. And that actually gives rise to a DNF, a disjunctive normal form, which is, by this theorem, logically equivalent to the Moby disk CNF. So the problem of finding all minimal pinning sets is equivalent to the problem of what might be called dualizing a positive conjunctive normal form to a positive disjunctive normal form, which I think is kind of beautiful. But sort of an aside. So anyway, just to kind of summarize so far, we have a loop, we have pinning sets. The pinning sets of the loop correspond to the satisfying assignments of the Moby disk formula. You can dualize, you can solve the problem by dualizing the Moby disk formula from a CNF to a DNF. And this pinning stack, which encodes all pinning sets, also encodes all satisfying assignments of the Moby disk CNF. And so so it too, so the partially ordered set of all the satisfying assignments of the Moby disk CNF is also the graph of all the possible game states. And we've cast the unpinning game in terms of Boolean logic. Okay, so okay, so let's talk a little bit more about this specific example from the unpinning game. So here was the unpinning game that we went through, and I claimed to you that that player 1 doing move 5 first was the optimal move, was the best move. So I'm now telling you that this is the Moby disk CNF. You have regional bygons 4, 6, and 10, all of which have to have a pin. Those are forced pins, forced true variables. You have a bygone for 1 and 2, a bygone for 2 and 3, a bygone for 7 and 8, and a bygone for 8 and 9. And the question is, why does player 1 win? Oh, and by the way, note too that 5 does not appear in any of the clauses. The region 5 does not appear in any of the clauses. So given this, can anyone tell me why player 1 wins?
Is there strategy stealing arguments where, assuming a player 2 victory, we can always just like player not play 5?
Say it again.
Is there a strategy stealing argument? So like suppose that player 2 wins, right? So if player 2 wins, then we just like choose or decide not to choose play 5 and then just steal player 2 strategy. I'm not sure if that actually works super well though. Maybe
there is a there is something that I think is sort of related to that. So you might be able to cast it in terms of an argument like that. Any other ideas? So
I'm thinking it has something to do with the fact that these are all like even length blocks of ores and they're like sufficiently disjoint, but I haven't exactly worked it out.
yeah, so maybe a hint is, so yes, maybe a hint is look at these two.
Oh, you can play symmetry over the two pairs.
Yeah. So after player one does 5, you know, whatever player, so if player 2 plays over here, then you play over here. So it's like a, yeah, it's a mirroring argument.
So this isn't strictly combinatorial in the general case, right? Can you think about it like that?
Yeah, I claim I would claim that it is because yeah, you know, it's all yeah, I make the claim that the Moby Disk CNF and all of its satisfying assignments is that is isomorphic to the pinning stack. One thing to keep in mind is that you have, you know, regions like 5, which are not part of any pinning stack or pinning set, and so you may have like unused variables in the CNF, and you do have to take those into account. But I don't know if that helps or not.
I'm not sure I necessarily understand your answer. Like I'm talking about like combinatorial in the sense of combinatorial game theory. Like, can we like consider? Yeah, maybe I miscommunicated there a little bit. But like, can you take two of these loops and merge them together? I guess you could. And I mean, maybe what you're saying is that this 1, 2, and 3 like sub loop could be split off from the 7, 8, and 9 one in some way that I'm not immediately seeing. Because like this is very reminiscent of NIM, and that's why I asked.
Yeah. So this is an impartial, you know, 2-player impartial perfect information normal play convention. So it falls into that framework of NIM. In particular, every game has a NIMBR, has a Grundy number. And yeah, I mean, you can take two disjoint, so you can take the game sum by taking two disjoint loops. But yeah, when you have a, you know, if you have a composite loop, it's not clear what the NIMBR is from that.
Right.
In fact, I think if you had a polynomial, if you had an efficient algorithm for calculating the NIMBR, that would contradict the theorem, or that would show that. Well, certainly it would show it couldn't be p-space complete, because you found if you can compute the NIMBR, then you can say who wins.
Gotcha.
Yeah. But yeah, no, that's one of the questions I was going to mention at the end. So, but yeah, player one wins here via that symmetry argument. Okay, so I want to talk briefly. I think I'm going to speed through this section a little bit, but I'm going to talk briefly about monogons and bigons, which are composite. Remember, I said earlier, the hard theorem of Haas and Scott is that if all of these composite monogons and bigons are pinned, then the loop is pinned. And I want to emphasize a subtlety here, that it's not just bigons that are cut up into regions. In particular, you can have a bigon that overlaps itself. In this example, I have a pin in, I have 3 monogons that have pins, and I have 3 pins, and that's it. And this is, I claim, not a pinning set, because basically because of this composite bigon that is what's called self-overlapping, looping over itself, and I can zip along that via Reidemeister moves. So I can do a triangle move to basically slide this crossing along until it comes out, and then continue sliding it around and reducing intersection. So the problem of computing the Moby-Disk CNF becomes a problem of deciding when a monogon or bigon is self-overlapping in this sense. So what I want you to pay attention to here is this yellow shape and its boundary, and ignore these 2 marked points. And the question is, when is such a curve self-overlapping? What do I mean by self-overlapping? Okay, I'm still going to be vague, but imagine you have this. Imagine you have a pancake, translucent pancake. It's infinitely stretchy, and you can slide this pancake around, and it's allowed to go over itself. In the sense of what's happening here, the pancake started embedded, and then I stretched it over itself, but I can't twist it. I can't twist the pancake. So which curves can we detect? Curves which have this property, which are self-overlapping? And thankfully, Shor and Van Wyck, and by the way, this is the same Shor from Shor's algorithm in quantum computing. They give a cubic algorithm that can check this for loops in the plane, and essentially they're trying to compute like a triangulation of such a pancake. So quick quiz: are the curves below self-overlapping? Can you realize them as the boundary of a pancake? Any guesses?
Like the first one on the left is not, and the second one from the left is.
Yes.
Third and fourth are a bit more complicated.
Yes. Yep. That's kind of the point. So the one on the left is absolutely not, because I would have to do a twist. The one on the right, I've just done like a Reidemeister 2, but it's done without a twist. Yeah, these ones on the right are harder to see. Turns out, yes, this one is, and no, this one is not. But the point here is just that, yes, it's hard to see. It's hard to see. And an additional subtlety is that a curve can be self-overlapping, but in multiple, like, combinatorially distinct ways. So this was a curve that was discovered by Milner, which is self-overlapping, but how you place the pancake is you have a choice. So here, violet is close to me, and red is far away from me, and I could imagine that this violet piece over here is a portion of the pancake that's close to me, and then it's kind of winding away from me, first around clockwise and then counterclockwise to the back. Or because of symmetry, I could have the pancake starting close to me on the left and then winding, counterclockwise and then clockwise to the back. So that's another hint that this is a non-trivial problem that Shor and Van Wyck have solved. By the way, this is open in surfaces of higher genus. So if you've thought about like tori or multi-hole donuts, and you ask these questions about self-overlapping curves, I believe it's not known whether there's a polynomial algorithm to detect this. So it's subtle. But in the plane, we can do it. Couple more examples. Here's a loop, and you see one of these self-overlapping bigons. And here is the corresponding clause, 2, 3, 5, 7, 8, 9. Yeah, yeah. So Stack Overflow, it says, feels like it's related to graph planarity somehow. Yeah. I mean, like the algorithm of Shor and Van Wyck is intimately tied to the planarity of the graph of the whole picture. It somehow becomes harder in higher genus. Yeah, I can say more about that, but I think I want to move on. Anyway, here's an example. You have one of these pancakes, and you have all of the Moby disks, and you can dualize this. You can compute all of the pinning sets. So here, for instance, the set 12, 9, 11, 10, and 14 is a pinning set. 8, 1, 4, 10, 14 is a pinning set. 12, 9, 5, 10, 14 is a pinning set. These are all of the minimal pinning sets. And this was computed with a program, an implementation of an algorithm due to Murakami Uno. It's a highly optimized, basically SAT solving algorithm that is converting from CNF to DNF as fast as possible. And this was like very fast, so very, very fast computation, highly optimized algorithm. Here's the one from the talk header. So here's the Moby disk formula from the one in the talk header. By the way, this one has a Moby disk that kind of makes this pretzel shape. That's how this was constructed. And I'm curious if anyone would want to guess how many minimal pinning sets there are for this loop, or like the order of magnitude. Are there less than 10? Are there 10 to 100? Are there 100 to 1,000? 1,000 to 10,000, 10,000 to 100,000, more than 100,000? I'm saying minimal pinning sets only, not even all pinning sets. E, C, D. Two swap, you nailed it. It's E. Zai, yeah, you're right. It's E. Okay, I said it too soon. It's E. So there's 10,775 clauses. And I'll just add that in terms of the implementations that we have right now, this process of dualizing is actually the fast part because of how optimized it is. So I think it took like under a second to dualize the CNF to the DNF. Actually, computing the Moby disk formula took like half an hour. So with Ryan Pham, a student of mine, we implemented this computation of the Moby disk formula, which relies heavily on the Shor-Van Wyck algorithm, and it's not very optimized. So it took half an hour on the previous loop. As Stack Overflow hinted, this shows that bounding the pinning number is NP, because if you can compute the Moby disk CNF in polynomial time, then you can check, you can verify pinning sets in polynomial time. You just check if a given assignment is in fact a satisfying assignment by plugging it into the Moby disk CNF. And that algorithm, by the way, is quintic because you have to you have to look at abstract bygons, which are roughly encoded which are proportional to pairs of crossings. So you basically look at, for all pairs of crossings, does that pair of crossings give rise to a self-overlapping bygon? So you have n cubed for each of the n squared pairs, or O of n squared pairs. I guess it's n choose 2. That's why it's O of n to the 5th, and that's why it's kind of slow. And sort of aside is that the Schur-Van Wyck algorithm relies on an initial embedding of the loop. So you start by embedding in polynomial time the loop in the plane, and you can do it really any way. The way that Ryan implemented it was using a very beautiful circle packing algorithm. And so I just wanted to show that because I like this picture. And this is commonly used for like making diagrams for knots, if you've seen those. Okay. All right. So now I want to get to the question that I was asking, which is the unpinning game p-space complete? I don't have an answer for this, but I will say some things about it. So I'll state it as a conjecture. The problem which takes as input a position of the unpinning game. So give me a loop in the plane, give me some pins. That's a position in the unpinning game. And tell me yes or no, does the first player have a winning strategy? That's a decision problem. We conjecture that that's p-space complete. It's not so important what p-space, so p-space is the set of decision problems which take a polynomial amount of memory to solve. And p-space complete problems are the hardest problems that are in p-space but are still in the but are, yeah, it's like the hardest problems in p-space. So for the purposes of this, yeah, so again, I don't want to harp too much on the definition here, but what I do want to say is this is like commonly the right level of complexity to look at for these two-player games. So Val gave a talk last week, I think, about Hexo. And there was some conversation at the end suggesting that Hexo is this is WebGoat Guy's game with basically tic-tac-toe or some version of tic-tac-toe on the grid, a two-player game. That it is p-space complete to decide winning strategies for that game. And Nate, I think next week we'll talk about Go, which is also a partisan two-player game played that's planar in some sense and is also p-space complete. So this is a common thing to aim for these sorts of games. I think I have a pretty good idea of what the right reduction is. It's a game called Nodecales. So let me tell you what Nodecales is. I'll define it first in terms of Boolean logic. Take a positive CNF formula and restrict two clauses that have exactly two variables, and start with all variables set to true. So the thing is satisfied because it's positive and all variables are set to true, and then start setting variables to false so as to leave a satisfying assignment, and the last player to move wins. You can also think of this as played on a graph. So here is an example of a game state. We start with the CNF with all of the variables true, and we start setting them to false. You can think of those variables and clauses as vertices and edges of a graph. The variables are the vertices, and the clauses are the edges. And the condition of satisfiability translates to the condition of vertex cover. So here, if I have 2, 3, 4, 2, 3, 4 is a satisfying assignment because if 2 is true, then this is true. If 3 is true, this is true. This is true. This is true because 2 is true. And this is true. And so the whole thing is true. And it's also a vertex cover, which is that every edge sees one of the vertex, one of the vertices from the cover. So the edge 1, 2 sees the vertex 2. The edge 1, 3 sees the vertex 3. The edge 2, 3 sees both 2 and 3. Every edge sees a vertex from the cover. Here in this example, player 1 loses because after they set 1 to false or remove 1 from the cover, player 2 removes 5 from the cover, and then player 2 has no other move. This is 2, 3, 4 is a minimal satisfying assignment, a minimal vertex cover. And so you're going down this post set of satisfying assignments, or equivalently this post set of vertex covers to a minimal point. Stack Overflowed asks, I guess in order for this game to work, the vertex cover satisfying assignment can't be minimal. Yeah. Yes. Yeah. Yeah. I mean, the input. Well, I guess I'm not totally sure what you mean, but the input doesn't. The input doesn't start as a minimal satisfying assignment. In general. Yeah, it does feel identical to node kills. Yeah, it does. because it's the same idea. You have the Moby to CNF, and you start taking you're it's the same game. It's the same game. 2 variables in each clause is not necessary, strictly speaking, but it is a restriction that will probably make the reduction easier, because if you don't add this restriction, then you have a harder thing to start with. So the way these proofs go, these reductions go, is you have an arbitrary starting position of the problem you're reducing from, in this case node kales, and then you have to model that with the Moby disk CNF. And so if you allow more freedom for the input problem, you're going to have a harder time modeling it. It's helpful for the input problem to be as restrictive as possible. Node kales is p-space complete. This was shown by Tom Schaefer in the 70s. And yes, the idea is that you want to build a CNF, a Moby disk CNF that models the input graph. And Zai, yeah, I'm going to talk about some of the difficulties. So this is roughly what you do. You would take every edge and you would put a bygone around it. Nate, that is a great question. Is it known whether planar node kales is p-space complete? No, to my knowledge, this is open, and that's crazy to me. I don't fully understand why, because so vertex cover. Okay, let me. I'll come back to your question. Anyway, so hold that thought, Nate. Anyway. This is the idea. You'd put a bygone around each edge. And now you have Moby disks that come from looking at the regions inside of such a bygone. And you want the Moby disk structure to basically model the clause structure of the input graph. Here is what it might look like if you manage to pull this off for the entire loop. By the way, this comes from our paper of showing that bounding the pinning number is NP hard, where we reduce from vertex cover. So we show in our paper that this is the exact construction. The minimal vertex covers of this graph correspond exactly to the minimal pinning sets of this loop. And that is basically the polynomial reduction from bound the minimum size of a vertex curve of this graph to bound the pinning number of this loop. The difficulty with the proof extending this to p-space complete and the unpinning game. So there's a couple difficulties. I think the first two are deal withable. So for one, there's parity conditions on the number of pins not inside any Moby disk. Here, after I build this loop, I have all of these extra regions that are created, and those become valid pins that I can remove in the unpinning game, and they don't directly correspond to variables in the original graph. So you have to control the parity of that. Parity is very important for games because you have these two players going back and forth. That is to say, even versus odd. So you have to control the parity of pins that are not in any Moby disk. You also have to control the parity of regions that are in like a few of the Moby disks, but not all of them. So, you know, every vertex corresponds to a region where a bunch of Moby disks intersect. But then you get like all of these extra regions where they're like, maybe they're in one Moby disk only, or they're in two Moby disks. And so you get the clause, the clause size is blowing up, and you have all of these parities to control as well. Is the other direction more trivial in the sense of, so stacked, is your question like, can I reduce node kale? Can I reduce the unpinning game to node kales? In general, that might be tricky because of the clause size 2 thing, but you could reduce it to generalized node kales, or what might be called like yeah. So there are p space. So yeah. So I think I think Schaefer calls it like G avoid CNF, and it's p space complete. You start with an arbitrary CNF formula, all variables set to true. Arbitrary positive CNF formula, all variables set to true, and you start setting things to false. Basically, no restriction on the clause size. Yes, that's still p space complete. Well, actually, yeah, that's p space complete. And anyway, yeah. So if you have an instance of the unpinning game, it reduces to that because of the Moby disk CNF. Okay, bigger challenge: non-planarity of the input graph. So node kales does not require the graph to be planar. Therefore, the first step of the reduction would seem to be take your graph and embed it in the plane so that you can construct this loop. And the problem is, if the graph isn't planar, you're going to have edges that are crossing. And that is really going to screw things up. So you're going to need crossover gadgets of some sort, for one. And yeah, as I mentioned, so Nate asked about planar node kales. This is open as far as I know. And further, it's open if you restrict to degree 3. I was trying to think what's the challenge with planarity when it comes to games being p space complete? And it seems to me that the fact that this game is impartial has something to do with it. So games like Hexo, games like Go, that are p space complete, they are planar in a sense, but they're partisan. You have different color pieces. Node kales has this impartiality where either player can make either move, and as far as I can tell, it's that impartiality that is partially what's contributing to the difficulty of proving that, say, node kales, the planar node kales is p space complete. I don't know though. I'm not an expert on this. But what's crazy to me, so this is a related problem that I just love. We don't even know if there's a polynomial algorithm for node kales on trees. We don't even understand trees when it comes to node kales. We understand paths, but even paths, already the situation is complicated. If you look at node kales of, okay, I'm digressing a little bit here, but if you look at paths of increasing length, and you look at their numbers, their Grundy numbers, the Grundy numbers do this crazy thing. They like jump around, and eventually they start repeating. So it becomes periodic, but it's like a period of like 50 or something. So paths already, it's like a non-trivial algorithm to decide the winner of node kales on a path, and we don't know how to do it for trees. I love this question. I think there's probably a polynomial algorithm for trees, but I don't know. Anyway, that's the challenge. Okay, one thing you could do to resolve this nonplanarity is you could allow loops in higher genus surfaces. So, given a graph, given an input graph for node kales, I can embed that in some surface of suitably high genus. And in other words, I can draw it in a surface of high genus, like a torus or a donut with enough holes, such that the edges won't be crossing. And then I can build a loop there. And then probably, and then at that point, it's just a matter of dealing with these parity conditions. I think that should be doable. I think that you can show that it's p-space complete if you don't restrict to loops in the plane, but if you allow the genus to grow. Okay, so just I'll end with a few questions. So as I mentioned, we want to optimize Ryan's implementation of the MobyDisk CNF. It's very slow right now. The SAT solving part is the theoretical bottleneck, because that's the theoretical exponential part, assuming p is not equal to np. So we'd like the polynomial part to be at least as fast as the exponential part. I'd like to have a nice user-friendly implementation of the pinning game. So with Araf Israk, another student, we've been working a little bit on that this summer, making some progress. Is there a MobyDisk formula for general multi-loops? So a loop is one curve. A multi-loop is like two superimposed loops. And you can ask all of these pinning questions for multi-loops. Turns out it's not clear whether there's a MobyDisk formula once you start doing that, which is totally surprising, and I can say more about that. But yeah, is there a MobyDisk formula for multi-loops? Simple multi-loops. So here, a simple multi-loop is like I take a loop and close it up, and it doesn't intersect itself. And then I take another strand and I close it up, and it doesn't intersect itself. And yet, maybe these two strands are, it's complicated in the way that they intersect each other. And maybe I have 3 strands or 4 strands. These are simple multi-loops. So with Eric So, we've proved that basically in this setting, pinning problems are still hard, are still NP complete. There is a MobyDisk formula in this setting. But we haven't thought much about the unpinning game. How does the MobyDisk formula change under Reidemeister moves? So I love this question. So it turns out if you take one loop and then you do a single triangle move, you can change the pinning number. So there's some way in which the MobyDisk formula changes in a non-trivial way. We'd like to understand like what is that? How can we maybe predict the new MobyDisk formula from the old MobyDisk formula? And this might be related to 1, because if we could do this well, then we could follow the MobyDisk formula through a curve shortening flow. Can the MobyDisk formula be computed in polynomial time for surfaces of positive genus? As I mentioned, we don't know if there's an extension of the Shor-Van Wyck algorithm in surfaces of higher genus. And then I already mentioned this too. What are the numbers? What are the Sprague-Grundy numbers that are associated to unpinning games? How fast do they grow? Can we find any patterns and so forth? Yeah, and then that's think that's it. I've got a couple references here that you can take a look at, including the poster that I shared earlier and also papers that we've written that will hopefully be published soon. Yeah, thank you. Any questions?
Thank you. That was very cool. I kind of want to actually try playing the game.
It's very fun. Yeah. I don't, yeah, so we don't have the app, we don't have the interface available yet, but we do have a bunch of loops and their MobiDisk formulas computed. And so we have like a catalog of basically a database of like 1,000 small loops and their pinning post sets, and their pinning stacks. But it's not really in a place where it'd be easy to play. But I will definitely let you know when we get that completed.
Sweet. Thank you.
Yeah, I'm not entirely sure I understand why parity is such an issue with proving piece completeness. Because it seems to me like you could just, because like player 1 is trying to make the game into like an odd length and player 2 is trying to make it into an even length. It seems to me like whichever one it's going to be, you can just add like an extra like removable pin that you can just get for free. Or wait.
Yeah. So I think that I think that if what you're saying is is true and basically resolves this first condition. You know, any regions that are outside of any MobiDisk, you can control that parity by just like adding something somewhere. But unless I'm mistaken, I mean I could be wrong, but if I'm not mistaken, like the bigger issue is these regions that are so like this. So if I zoom in here, like this region that's like close to a vertex and it's in 2 MobiDisks, but not all 3 of them at this vertex. That is acting on the clause in somewhat of an unpredictable way, because it's like you're affecting these 2 edges, but not all of the edges that you should be affecting. And so I think what you would want is you'd want to have a response, right? Like player 1 plays here. What does player 2 do? And maybe you create like a mirror, you know, so this region maybe corresponds to another region up here or something that then player 2 always plays in. But you have to like get the geometry right to make sure everything has a response of sort of the appropriate like number of clauses or whatever that it's appearing in. But I could be wrong. I mean, maybe it is easy. I'm not totally sure. I would love it if you could prove it.
Have you thought at all about like sort of the opposite game, like you could call it, I guess, the pinning game, where you add pins and the goal is to either make or not make it a complete pinning set?
Have not thought about that, other than we have realized that there's many variations of the games you could play. Yeah, you could build up towards a pinning set, be the first one to pin it. You could play these games like misère, like you, instead of being the last one to move, you want to be second to last one to move. Yeah, I mean, I think there's many games. Oh, and there's also like, okay, here's a game I really like. Okay, start with a loop and start unpinning it. And on your turn, your turn consists of do as many Reitermeister moves as you can to try to reduce intersection. And if you succeed, then you get some points. So if you succeed in like reducing the intersection by 2, then you get 2 points. If you succeed in reducing the intersection by 1, you get 1 point. And then the game keeps going. You then at the end of your turn, you remove a pin and you pass it back to the other player who does Reitermeister moves and tries to reduce intersections. And if you start with a loop that has an odd number of crossings, then it's guaranteed to not end in a draw. And so, yeah, what one player is always going to have is going to have more crossings. Yeah, I think it's a better. I think that game would be more fun to play. That game would be really cool. I think the theory of that game is probably harder. So understanding the theory of the unpinning game would lend itself to understanding the theory of that game. But yeah, there's any number of possibilities for pinning games and unpinning games that I would love to talk about and study. Non-sharpness of games like Snort and Go. What do you mean by non-sharpness?
Like, so sharp, anybody can correct me if I'm wrong here. I don't usually use this word, but I think chess players call like certain variations sharp insofar as deviating a little bit from it means you're just going to lose. Whereas in Go, like you can sort of have a bit of a lead and accumulate a lead, or at least there's a feeling that you can. Whether or not this is a formal idea, really, I'm not sure, but
it has something to do with like the backtracking length in the game tree or something like that.
Something like that. Yeah, you could probably formalize it if you wanted to.
Like, probably the better way to think about it might be like if you can lose with one move, if you can make a really bad blunder and immediately lose, then it's a sharp game. But if you can like if you have some leeway, then it's not sharp, not really.
Okay. Yeah.
Maybe like a more generic way is to think about the slope of the gradient around your current position game space. Right. If it's steeper, then it's sharper.
Okay, for a sort of combinatorial notion of gradient. Something.
Yeah, something like that.
Yeah, so yeah, and I also agree that yeah, adding this idea I just described is probably less sharp.
Yeah, I kind of slightly prefer non-sharp games.
I think I do too, yeah. You don't like to see an immediate loss. At least until the end when you feel like it's not going your way anyway. But also, I think it's a little bit of a relative notion. Like, so do people say chess is not sharp because, if I'm playing Magnus Carlsen, the Stockfish knows I'm losing by like move 5. But
it definitely
still...
exists on a spectrum of some sort. But like, yeah, I think of chess as a rather sharp game insofar as like, well, compared to Go, compared to Go, I guess I think it is because you can just like blunder and get checkmated. But
Yeah.
in Go, like, I mean, maybe a giant group dies, but most of the time that's not what the game's about, and you're just trying to do little local situations. And if one dies, then maybe you're gonna start losing, but it's not as immediate.
But it also occurs to me that if a game is like too non-sharp, then it can't be that hard because it's somehow like your moves don't matter that much. If you can sort of always, if you can always come back, then the game is maybe not that interesting. So there's probably some balance.
Those games are typically longer. like Go takes much longer than chess for like a game to play out. So you kind of like you have to make several good moves, like better moves than your opponent. You have to outplay your opponent like a few times in a row to win, if that makes
Yeah,
sense. Yeah.
that's nice. Yeah, yeah, yeah. That's probably a good way to say it. It doesn't just take like one. Yeah, one good move can swing things a little bit, but not the whole way. You need a few of them. I love Mario Party. Haven't played that in a long time. Well, any other questions? Otherwise, I'm happy to end it here. I went longer than I wanted to.
Thanks a lot. I appreciated it.
Yeah,
I like this game, and I'm looking forward to trying it.
yeah. Let's talk about it more. Yeah. Thank you all for coming.
Thank you.
Yep.